Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 5, Applying Newton's Laws, Video 3. Today's topic is Using Newton's Second Law, Dynamics of Particles, Part 2. Objectives are to understand problem-solving strategies and be able to solve a variety of dynamic problems. Let's continue with more examples. A toboggan loaded with vacationing students, total weight W, slides down a long snow-covered slope. The hill slopes at constant angle alpha, and the toboggan is so well waxed that there is virtually no friction. What is its acceleration? So first, you sketch the situation, then you draw a free body diagram. So for an object on a slope, we usually have the x-axis is parallel to the slope. In this case, going down is positive, and perpendicular to the axis, we use that y, so going up as y. So from here, is one thing I wanted you to pay attention. A good road sign is to be sure that normal force comes out perpendicular to the surface. Normal force is never straight up and down, always perpendicular to the surface. Let's use Newton's second law. Sum of the force in the x direction equals max. In this case, the force in the x direction is W sine alpha. And sum of Fy should be equals to 0 because the toboggan is not moving in the perpendicular to the slope. Since we're only asking the acceleration, and acceleration is in x direction, we don't even have to consider the y direction. So from x direction, we can solve ax equals W sine alpha over m. W equals mg, so m and m cancel, ax equals g sine alpha. What does this tell us is that acceleration does not depend on the mass. This means that any toboggan, regardless of its mass or number of passengers, slide down a frictionless hill with an acceleration of g sine alpha. In the special case, if alpha equals 0, that means there is no incline, then a equals 0, so there shouldn't be any acceleration. In another special case, when alpha equals 90, like vertical, then the toboggan should be in free fall. Another example, two bodies with same acceleration. So you push your 1 kilogram food tray through a cafeteria line with constant 9 Newton force. As the tray moves, it pushes on a 0.5 kilogram carton of milk. The tray and carton slide on a horizontal surface that is so smooth that friction can be neglected. Find A, acceleration of the tray and carton, and B, the horizontal force that the tray exerts on the carton. Let's take a look. So here is a tray and here's a free body diagram. To find acceleration, we treat the two as one object. The reason for that is we get rid of the force. If we treat two as one object, we get rid of the force in between. So make it easier. So in this case, the net force in the horizontal direction is just F, the one you applied 9 newtons. And the y direction is normal force and weight. Normal force and weight cancels. Anyway, we're just trying to find acceleration in horizontal direction. We don't really even concern us with y in this case. So this F is accelerating both carton and a tray. So we have to add the mass together. From here, we can find acceleration equals 9 divided by the mass of the carton plus mass of the tray. So acceleration is 6 meters per second squared. Next one, we have to find the horizontal force that the tray exerts on the carton. That is the force in between. To find the force in between, we have to individualize each object. In this case, I want to do milk carton. Why do I do milk carton? Because there is less force acting on the milk carton. Take a look on the milk carton. The horizontal force is from the tray on the carton, and there is a vertical. This vertical cancels. So we don't even have to concern us with the vertical forces because they are asking the horizontal force. Horizontal force equals m carton times acceleration of the carton. Acceleration of the carton is 6. So that gives us 3 newtons. By the way, ax is the acceleration of both tray and a carton, 6 meters per second squared. So we get that, and we get the force. Let's see about the results. So we treat two objects as one in order to solve for acceleration because the two objects have the same acceleration. We also choose to treat the milk carton to solve the forcing between the carton. That is because the tray has less horizontal force acting on the carton than because there is less horizontal force acting on the carton than on the tray. On the tray, there's a force, your hand, that's one force, then the carton also exert a force on the tray. So there are two forces on the tray, make it a little bit more complicated. Let's take a look at another example, two bodies with the same magnitude of acceleration. So an air track glider with mass m1 moves on a level, frictionless air track in a physics lab. The glider is connected to a lab weight of mass m2 by a light, flexible, non-stretching string that passes over a small frictionless pulley. Find the acceleration of each body. These two bodies, because they are connected by the string, so they have the same acceleration. And the tension in the string, kind of similar to the last question. So here is the sketch of the situation, the glider and the mass. That's because they have the same acceleration. Let's treat the two as one. To draw a free body diagram, we know here is the net force. The force that is accelerating both bodies is m2g. That's a net force. And the both bodies' mass is the two mass added together. So we treat the two objects as one. From here, we know sum of the force equals to m1 plus m2a. So we can find a equals m2 divided by m1 plus m2g. So this is acceleration of both the mass and the glider. Next one, let's find tension. To find tension, tension is the force in between. We'll have to treat each object separately. So which one is easier? Let's talk about M2. M2 has two forces, the tension going up and M2G down. Now, what is the force in the glider? There's up and down force, these two cancels. So the net force is just horizontal tension. So the glider is easier. Free body diagram, to find tension, choose the glider because it has only one horizontal force. So that horizontal force equals M1 times AX. We already know AX equals to M2 divided by M1 plus M2 times G, so we can find T. So T equals to this. So now consider the result. What can we conclude from that? We see acceleration is less than G. That makes sense, right? Acceleration is less than G because there's a tension going upward to hold M2. And it's also because the force m2g has to accelerate both mass, not just m2. That's why acceleration is less than g. Next one, the tension. Look, the tension does not equal to m2g. As a matter of fact, the tension is less than m2g. If tension equals to m2g, what would happen? If tension equals to m2g, m2 wouldn't be accelerate at all. M2 would be in equilibrium. But we know that's not true. We know they are both accelerating. Special cases, if m1 equals to 0, then tension would be 0. m2 would be in free fall, so acceleration equals to g, or negative g. Next one, if m2 equals to 0. If m2 equals to 0, then m1, there is no tension to pull m1, so m1 would be just sitting there by itself. Check your understanding. So suppose you hold a glider in example 5.12 so that it and the weight are initially at rest. You give glider a push to the left, so you pull it backwards, then release it. The string remains taut as the glider moves to the left, comes instantaneously to rest, then moves to the right. At the instant the glider has zero velocity, what is the tension in the string? Is it greater than the last example? Is it the same as the last example? Or is it smaller but greater than 0? Or is it 0? Think about it. You can compare this, as a matter of fact, with an object in free fall. So No matter what the instantaneous velocity of the glider, its acceleration is constant, and it has a value found in the last example. So in the same way, the acceleration of a body in free fall is the same whether it is ascending, descending, or at the top, at a high point of its motion, or at rest. That's the point at rest. So the answer is the same. That's it for today. Thanks for watching. See you next time.